Now we will see the elastic potential energy in a stressed wire. If you have work is done along the length of the stressed wire, then some elastic potential energy will be stored, and so we will try to find out the elastic potential energy, that is half the stress into strain into volume. So यदि हमें एक वायर दिया हुआ हो, उसको स्ट्रेस करना है, अप्लाई कुछ फोर्स लगा के उसको उस वायर को स्ट्रेस करें, तो कुछ वर्क डन करना पड़ेगा, और दैट वर्क इज डन अगेंस्ट द इंटरमॉलिक्यूलर फोर्सेस ऑफ द वायर, एंड दैट वर्क डन इज स्टोर्ड इन द फॉर्म ऑफ इलास्टिक पोटेंशियल एनर्जी इनसाइड द वायर. So if you try to write this, if we stressed a wire, work is done against the intermolecular forces of the body, and this work done and this work done is stored in the wire in form of elastic potential energy. Elastic potential energy. Elastic potential energy. Now, if you have a wire of length L and cross sectional area of the wire is A, and if you apply force F, then there will be some increase. There will be some increase of length of the wire. Suppose here there is a wire, thin wire. This one is clamped, and if you apply some force, if the length of this wire is L, and area of the cross section is A, area of this cross section of the wire is A, small a. Then under the action of this force, the length of the wire increased by a length say small l. Now, in this condition, the longitudinal stress in this situation will be F by A, and longitudinal strain in this wire will be L by L. Now the force required to increase Now, the force required to increase the length, increase the length of the wire, of this wire, length of, increase the length of this wire by L is given as we will have an expression of Young's modulus y equals to F times F by A over L into L by L. So F equals to, F by A equals to, F equals to y times A L over L. This is the force which is need to increase the length of wire by L. Now, the work done by this force is given by now if further the length of the wire is increased, length of the wire is increased by dl, then work done is dW equals to F dl. Now the value of F can be written from here. So F equals to y times A by L into L dl. Now the total work done to increase the length from 0 to L. Now the total work done we calculated as taking the limit from 0 to L, YA over L dl. Now we will integrate this expression and find out the value of work done. Now while A and L is a constant value, the length of the wire, this is the cross sectional area, that is small a, then small a, is also a constant, and y is a coefficient of elasticity. So it will be taken out from this integration A over L 0 to L. Now W equals to YA over L L square by 2. The integration of L dl equals to L square by 2. Limit is L to L. Now ya over n and half is taken out, half. This one is L square minus 0 square. Now this can be written as half y, and here is the L square, so we will choose, we will take one L and this L, and one L here, and again we write one L capital and into AL. So this y times this Young's coefficient of Young's modulus times the fractional change in the length of the wire gives the value of the stress. That is the stress. This y times L by small l by capital L gives the value of stress. This is the fractional change, the strain in length head. And this is AL, area times length, this is a volume. This is the volume of the body or wire. This work done for stretching the length L, this work